will start with the concept, which is your MOSFET. So you people know, right, ki, in our phones, otherwise laptops, many of the chips are made up of this MOSFET are always, otherwise CMOS technology, okay? So now every year, 10 to the power of 20 transistors are made every year. So what is our global population is something around 1000 crore. So it is something like 10 to the power of 10 people. Okay. So for every individual, if you see overall 10 to the power of 20 transistors are made every year. So one individual, you will get 10 to the power of 10 transistors. So if you observe carefully, the companies that produce the chips are your TSMC, your Samsung, Intel, Global Foundries, like that. And companies that design the chips are like Qualcomm, Nvidia, and this Apple. So this fab companies will help to this design part, and we will get our final output. Okay, that is our chip. So let us now go to our MOSFET concept. So, and you also make a point key right now we are using the FinFET technology. But before understanding the FinFET, you should definitely know your MOSFET concept because this is very much similar to FinFET. This is like an evolution that is happening in our world. Okay. So your MOSFET is nothing but your metal oxide semiconductor. Please kindly note in your notes so that you can revise it later on. So your metal oxide semiconductor field effect transistor. So it is in the hierarchy like first you will have a metal. On bottom of it you're going to have some oxide and a semiconductor. So if you observe here your metal oxide semiconductor. So then why they have given you this field effect transistor? Means there is some electric field that is induced when you are going to apply some kind of voltage at drain or source. So that is helping you to get some kind of current in this transistor. So whenever this current is getting passed, you can say that whether the transistor is on or off. Okay. So let us now go to our MOSFET, this entire diagram. So you just first start with your substrate. So I'm going to draw my NMOS. Here my N is nothing but my N-channel MOSFET. Okay? N-channel MOSFET. So your MOSFET is generally a four-terminal device. So it is a four-terminal device. So what are those terminals? So the first is your source and your drain. And if you observe carefully what I've told you, you also consists of an oxide. On top of it, you will have a thin layer of a metal. So this is your metal that is made up of, so that terminal that is made up of metal and that terminal you call it as gate. Okay. And your oxide is mostly made up of SiO2 and your substrate here is made up of silicon. So now since this is an NMOS, you have to use a P-type substrate. And here I am denoting your P minus because this is lightly doped P-type. So doping means what? You are adding some kind of impurities to an intrinsic semiconductor, otherwise a pure semiconductor. So now I have mentioned a lightly doped p-type. Means what? You are adding like something like two or three p-type in thousands of transistors. So that is called as a lightly doped p-type. If it is heavily doped, you are adding more number of holes in that semiconductor to make it heavily doped p-type semiconductor. So now I have mentioned it a P minus substrate. This is like kind of bulk. So I will denote this terminal as my body. Okay. So now what are the four terminals of this MOSFET? So the first one is your source and the second one is your drain and your gate and your body. So we call this MOSFET as a symmetrical device because you can interchange both this source and drain. Okay. You can interchange this source and drain. So you may ask, then how I will say whether it is an NMOS or PMOS. So if your drain is having higher voltage than your source, then we call it as a NMOS. Okay. So someone have given you just like your drain and your source and something like this sort of, and you have to understand whether it is an NMOS or PMOS. In that case, if your drain is having higher voltage than your source, then we call it as an NMOS. And if your source is having higher voltage than drain, then we call this transistor as a PMOS transistor. Okay. So now to this source and drain, you have to induce a N plus region. Otherwise, you have to dope the N plus, otherwise more number of electrons, heavily doped electrons, so that you will get the N plus region here. So this is your N plus and this is your N plus. Okay. Finally, this is your MOSFET. If you observe here, this is your metal, mostly made up of some kind of aluminum. And previously, we have also used a polysilicon structure. So this is metal and this is your oxide, which is very thin layer, something around very less nanometers, not much high. So this is like really thin, okay? And here where you will get your channel, okay? So you will get your channel here. So this is your NMOS. So this surface, whatever that is there, so that is very important because you are going to apply some kind of voltage on top of it. So now you have to do some kind of analysis at this surface. Let us go to the next, which is your MOS stack. If you observe here carefully, this is your metal and this is your silicon dioxide and this is your silicon, which is made up of, which is a substrate, and this is your silicon. And if you observe here carefully, your oxide is SiO2. So that is what the advantage here, because since your substrate is silicon, you can directly do some kind of oxidation to this substrate. So you will do some dry oxidation and wet oxidation. Somehow you will get your SiO2. So that is what the advantage of this silicon. Okay. So now on top of it, you have added the metal. So this is your metal oxide interface. And this is your SiSiO2 interface. And this is called as your surface. If you observe here carefully, your SiO2 is your insulator. Okay. So now in this case, this is your metal and in between some kind of dielectric, which is your insulator. And on bottom of it, you're having some kind of silicon. These are like two metal plates. In between that, you're having some kind of dielectric. So this will act as a capacitor, okay? So we call this metal oxide semiconductor without drain and source as a MOS cap, otherwise MOS capacitor. If you add drain and source to this MOS cap, in that case, you will get your full MOSFET, okay? Your full MOSFET. You all know the reverse bias and forward bias concept, right? Just I will write. So this is your PN junction, okay? So if you are applying a positive voltage to your positive terminal of your voltage is connected to your P type and your negative terminal of your voltage is connected to N type. So we call this as a forward bias. So in forward bias, what will happen? Your depletion region, whatever that is there at this junction will decrease. So you just remember this point here, depletion region will decrease. Okay. But in reverse bias, your depletion region will increase. Okay. So in between this P and N, you're going to have some kind of junction. Whenever you're applying a reverse bias, your depletion region will automatically increase. So you just remember this point. You will understand why I'm saying that. So this is your N plus, and this is your N plus. This is your P minus substrate, your N MOS. You're having your oxide, on top of it, your metal, and this is your gate, and this is your substrate, and this is your drain, and this is your body. Okay. And there are two junctions that is been there here. The first one is your source body junction, because your body is made up of P type and your source here is made up of N type, right? So obviously what you're having here, your PN junction. So I call it as my source body junction. Here I call this as a drain body junction. Okay, drain body junction. So let me apply a potential on top of it and like on gate, and let us see what will happen to the channel region. Okay. So first what I'll do is I'll keep my drain, my source and my body voltage is 0, and I only apply some kind of voltage on top of gate, something which is greater than 0. I'll apply some voltage on top of this gate and let us see what kind of, regions you will get. Okay. So I told you that in a this MOSFET is acting like a capacitor, right? And in between there is some kind of dielectric. So this top charge you just mentioned it like plus Q. So this is your CV. So you all, I hope you know this Q is equals to CV formula. On bottom plate, you're going to have negative charges. So this is minus Q, which is your minus CV. Okay. So now I will apply some kind of voltage on top of this gate. So this is my N plus. This is the oxide. On top of it, there is a metal, and I'm going to apply some gate potential, which is greater than 0. Now let us see what will happen. This is connected to ground because I've given 0. Your Vs is 0 and your Vd is also 0. And my body is also connected to ground. So imagine that there are three possibilities that you can do at the gate terminal, which is first your Vg is less than 0. And second one is your Vg is very small. And third one is your Vg is greater than your Vth. Since your source terminal potential is 0, I can also write as VGS, because VGS is nothing but VG minus VS. Your VS is already 0, so your VGS is obviously it will become VG. Okay, so first I will apply my negative voltage, which is VGS less than 0. So if I apply a negative voltage at this gate, what will happen? Generally, what a negative ion can do, it will attract the positive charges, right? So if I'm applying some negative potential on top of this gate, it will try to attract the positive charges. So in P type, generally what you will have holes, right? So this negative ions will attract the holes. Okay, so you will get holes at these charges. If you observe here you're going to have P minus, right? Because why? It is lightly doped. Lightly doped means you're going to have like less number of, what I can say, holes. But if you observe at the surface, there is more number of holes that is been accumulating. Means it have converted from P minus to P plus, right? Because at the surface you're having more number of holes. That means what? It is heavily doped P type only at the surface, not in the bulk. Okay. So that is what I meant to say. If you observe here, there is accumulation that is been happening here. Okay. Accumulation of holes that is been happening here. So we call this region as a accumulation region. Accumulation region. Why? Because there is accumulation of holes at this surface. And we call this as your channel, right? In this channel region, what you're having? You're having your holes. So do you think that there is any kind of conduction that will happen, conduction of current that will happen in this region? The answer is no. Why? Because this is your drain, this is your source, and here you're going to have your holes. Okay. So this is a channel region. So this is your n plus n plus. So what is the um majority of carriers that presents in this n type, which is your electrons. And here also you're having electrons. But if you observe, this is your holes. I'll try to do one thing. This is my n type. This is my p type. So since this is looking like a pn, I will try to draw a diode. So two PN diodes that are connected back to back. You people all know, right? Your diode is always
BJT.
unidirectional. So your diode is always your unidirectional. It will flow a unidirectional current. So what I'll try to do is I will try to pass my current like this. Okay. And that too from P to N. Okay. Here it will pass, but here this will open. So ultimately there is no current flow in between this uh, drain to source. There is no current flow in between drain to source. Or else, since the majority carriers in this n type is electrons, and your drain and source is consisting of electrons, but in between you're having holes, so there is no movement of electrons from drain to source. So by this also you can say that there is no current flow in between drain to source when your VGS is less than 0. Okay. And since there is accumulating of holes at the surface, so you call this region as accumulation region. Okay. So let us now try to go to the next case. So that is your VGS, which is greater than 0, but it is like really small. Okay, not very high voltage. So now what I'll try to do is I'll apply small voltage on top of this gate. So how it will look like. So this is my oxide and this is my gate. And I'll keep my source and drain grounded. Okay.
Can we say the formation of BJT in the previous case?
It's not BJT, right? It is MOSFET. Okay, this
No, no.
one.
Oh, yeah.
See, this is your N plus N P region. Okay. So what
Yeah,
is
when
your N?
both diodes are connected in back-to-back fashion, we can say the BJT, right?
You can say, but can you say that here there is any current flow? So that is what the point I want to make it here. I just don't want to make any kind of BJT point here. I wanted to say that there is no current flow in this, in between this drain and source. So that is what my point here. Because if you see, if your diodes are connected like this, I can say that there can be a flow of current. But now here the diodes are connected from back to back,
Right.
right? Okay,
Yes, ma'am.
that is the case. So now if you observe here, I have applied a small voltage on top of this gate. Whenever you're applying a small voltage on
Is
top
this the
of this
first class
gate,
of this course, ma'am?
sorry, this is my first class. I don't know about yours.
Okay. So this course, what is the structure of this course, ma'am?
Team will let you know. I'll ask the team and team will let you know, sure. Okay?
Okay.
Okay. So now you are applying a small potential on top of this gate. So if you try to do that, what is your gate is having? Now your gate is having positive ions. So what this positive ions try to do? It will try to repel your holes which is there at your surface. Okay. So at the surface, what you're having? You're having some kind of holes since this is made up of p type. So now it will try to repel these holes. Whenever your ripple is getting sorry, your hole is getting repelled, in that case, it will leave some kind of negative ions. Okay, negative ions in between this drain and source. Since I'm applying very small potential at the gate, so I am having this negative ions at the surface. So how now it looks like? This is your N plus, your N plus, your negative ions. But if you observe here carefully, in N plus region, you're having electrons. In N plus region, you're having electrons. You may say that my electron is a negative charge. Um, and my drain and source are having that, and in between also I'm having negative ions. So there should be a current flow, right? You may ask that kind of question, but
It's
in
an ion.
between, it is an immobile ion, right? So it cannot move. So since it is an immobile charge, it cannot move. So there is no path that a current can flow. Okay. So in this case also you are not having any kind of current flow in between this drain and source. Okay. So now, so we call this as your depletion region. So whenever you're applying a very small potential at the gate, so you call this region as your depletion region. Okay, just remember this is your second case. And your third case now is your when you have applied some kind of large positive voltage on top of this gate. Large positive voltage. So this is your N plus, this is your N plus, and this is my oxide. On top of it, there is a metal. So now I am applying some kind of potential on top of it. So this is my source and this is my drain. So now what I'll do is I'm applying a large potential, right? So you may say that, ma'am, it is like previous case only. Yeah, it is like previous case only. So first what it will do, it will repel almost all holes that is there at the surface. So the maximum holes got repelled. So it have reached to the maximum region. So now it have reached to the maximum region. Now we are not going to have any kind of repelling here. But still, if you apply a large voltage, you should get some kind of electrons, right? Now, what it will do is it will try to take some electrons from this drain and source. Okay. So now you will get some kind of electrons from this drain and source because you are applying a large potential at your gate. So it will tend to move some, like your electrons will tend to move from your drain to channel. You may ask why. Because there is some kind of diffusion that happens at this source and your channel region. Diffusion means what? Carriers will move from high, but I mean high charges, high concentration to low concentration. If you observe here, your P type is having less number of electrons, but your source and drain is having more number of electrons. So now your carriers will move from your source to drain through the diffusion thing, and you will get the electrons at the surface.
Ma'am,
Okay.
excuse me.
Yeah.
Yeah, is it not attracting minority carriers from the body?
See, minority carriers, if you think like that, your minority carriers will be like 1 in a million. So if it is there in bulk, you cannot get that from the bulk. So that is why it will take the electrons from your source and drain. So that is what happens here. So I also got the same doubt, but that is not the case here. There will be some kind of diffusion that happens at this surface, and that is how you will get your electrons at the channel region. Okay.
Okay, ma'am. Okay, ma'am.
Okay. So there is a book called Razavi. So after completion of this class, definitely you just refer this Razavi book for analog part. For digital part, you can refer this LN one, and then yeah, I'll tell you tomorrow the book name. And recently I've referring this
Boris
was in.
Mano.
This is also a good book. So
Boris
yeah,
Mano, I think.
Morris Manu you can use, that is for digital electronics, but I'm telling about digital IC design and fabrication. For that part, you can use this Voisin book. So that is really good. So, okay, coming to this concept. So now you're going to have some kind of free electrons. If you observe here, in your N plus, you're having your free electrons. So that free electrons will be there in your channel region. Okay. So now if I try to draw this, this is my drain and this is my channel region. This is my source, this is my drain and this is my channel region. In this channel region, now I am having some kind of electrons. And your source is made up of N plus and your drain is made up of N plus. So ultimately there is a creation of conduction path in between this source and drain. Okay. So can someone tell me, this is my source got this ground and my drain got grounded. So will there be any current flow in between this source and drain? This is my question.
No, ma'am.
Why?
There is a zero potential difference.
Okay. So since your source and drain is zero, so your voltage difference is zero. So ultimately your current will be zero. So the current flow will be zero like this. Okay. So even though you got your conduction path in between your drain and source, still there is no current flow because there is no potential difference. So there is another point that you should remember is your electric field will be always in the direction of high potential to low potential. Okay, high potential to low potential. So what are the three regions that I've told till now? So the first one is your accumulation, and the second one is your depletion, and your third one is your, okay, your third one is now your inversion. Why? Because your channel now fully consisting of electrons, right? But previously, what is your substrate? That is your p type. But if you observe your surface, it is consisting of full of electrons. So in this case, it have converted from p type to n type. So it got inverted to n type. So that is why we are calling this as a inversion mode of operation. So we call this third region as your inversion region. And this will happen whenever your VGS is greater than your VTH. So here your VTH is nothing but the minimum potential that you should apply at the gate to create some kind of channel in between your source and drain. This is nothing but the minimum voltage that you should apply at gate to get a channel between drain and source. So that is our definition in NMOS. So the third case you're having is your inversion. Okay. So first, in this case, there is no current flow. So your transistor is off. In this case, no current flow, transistor is off. Here, there is some kind of inversion. So your transistor is on when your VDS is your greater than zero. Whenever you are applying some kind of potential in between this drain and source, in that case only, there is um, on of this transistor. Okay. Whenever your VGS is less than or is equals to VTH, so we call this device is in off region. Device is in off because there is no channel formed. So whenever you're applying the voltage which is greater than VTH, in this case your N channel is formed and your device is on off. Okay. And also you should have some potential. In that case only there is a flow of current. Since you're having a conducting path in between your drain and source, so I'm calling it as my device is on. Okay. So let us now, yeah, go to this NMOS transistor. How the electrons will flow? Is it from source to drain or drain to source? How your electrons will flow in your NMOS? Can someone please unmute yourself and answer this?
I think from source to drain.
Yeah. You can also think in this way, ki your source will generate your electrons and your drain is like your destination point. So that is where your electrons will come. So that is from your source to drain. In other way, you are applying some positive potential at the drain. So what it will do? It will attract the electrons. So ultimately your electrons is moving towards your drain side. So that is nothing but your free electrons direction is from your source to drain. So if your free electrons direction is from source to drain, your current direction have to be from drain to source because your I is equals to Q by what? Time, right? So your Q is now your electrons, which is negatively charged. So this both are like moving in opposite direction. So if your free electrons is moving from source to drain, so in this case your current direction will be from your drain to source. And your NMOS, your VD have to be always greater than your VS. So your electric field direction will be always from your high potential to low potential. So that is from your drain to source. Okay, so that is the case here. So let us now see the representation of this NMOS.
Ma'am, can you repeat the last point?
This one,
Yes, ma'am.
yeah, see, your electric field is generally from high potential to low potential.
Okay, okay,
Okay,
support electric field. Okay, right,
okay,
right, got it.
okay. See, I just explained again. So your electric field will be from high potential to low potential. Since in NMOS, your VD always have to be greater than VS. So now your higher potential is your drain. So electric field direction will be from your drain to source. So that is the case here. So let us now come to the representation of your NMOS. So that will be like this. You're going to have your gate, your drain and your source. So now your current direction will be always from your drain to source. So I will represent it like this. And here the point to note here is your gate current will be zero because there is a insulator in between. So this insulator won't allow you to pass the current from your gate to your body. So your gate current is ultimately zero. So only current that exists here is your ID. Okay, that is from your drain to source. So what have to be your body current, I mean body direction, current direction. If this is NMOS, is it this side or this side? You can just say it ki whether it is less than or greater than. Otherwise from body to channel, otherwise channel to body. What do you think?
Body to channel the electric field, ma'am.
Yeah. Why? May I know why?
Because in NMOS we are using P substrate and
Yeah.
it is majority of holes.
Okay.
So the channel is of electrons and electrons are moving from uh, like
Yeah, you're right.
body.
So, okay, you're right, you're right. So your body is your P type and your channel is your N type. So now if you consider it as like your diode, it will be from your P to N type. You just simply remember in that way. So now this direction is from your body to your channel. So that is the case here. So let us now come to the 3D view. I don't know how it will come, but I'll try to draw this 3D view. So this is my metal and metal is made up of a polysilicon, otherwise some other metal you can use. I think right now they are using metal, but previously they have tried with polysilicon. So that is why evolution has happened. So this is your metal and this is your oxide. And this is your like N plus and N plus diffusion source and drain regions. And this is where you will get your source and drain. So this is my substrate, which is your P-type substrate. Okay, P-type substrate. So this is the channel length. I'll consider it as L, and this is your W. So as a design engineer, you should definitely focus on your W and L. Do you people know why we are more focused about this WL? Why we are not focusing on the other parameters as a design engineers? What do you
Because
think,
all
my?
this,
Yeah.
the value of current depends on these two parameters.
Uh, okay, it is right, but can you think something about area and explain?
This is the portion through which we can control the whole device, ma'am.
Yeah.
And because of that, that is the most important thing. And I have one more doubt, like the width of the device and width of the channel both are same. Like if we are having source, drain, and gate all together, like if we
Yeah.
as per design perception, like which one we will consider as whole device, we will include the like source and drain also in a consideration of device, or just the channel width or length.
Your source and drain are like really small. So the ultimately, whatever the gate part where you will get your channel is the major part that you should consider. So that is your L. So in industry, you used to say like 3 nanometer, right? So currently we are working on 3 nanometer. So that 3 nanometer is nothing but your channel length. If you try to reduce that channel length, so your device will work fast because you're reducing your area. What is the area of this gate part, which is your WL, right? Whenever you try to reduce your W and L, your area will ultimately decrease. So imagine that your area of your transistor is decreasing if this is what area they have given to us. So now with 100, otherwise some 100 square nanometer square, this is what the area previously we are having. Okay. So now we got decreased to it to the 50 square nanometer square. So they have given us this area with 100 square nanometer square area transistor. If we can insert 1000 of transistors with 50 square nanometer square area transistor, you can fit something like 5000 transistors. If more number of transistors we can insist on the single chip, we can increase the functionality. Okay. So that is what the case here. So ultimately, as a design engineer, you should see your W and L as a parameters, and you should try to decrease the W and L. Obviously, there are some kind of disadvantages you will face, but that we'll see later on. But these are the parameters that you should focus on. Okay. So let us now see this current equations. Okay, fine. Current equation. So this is your N place and this is your N place. And this is your oxide. And I've applied a gate potential on top of this gate, which is greater than VTH. Now I say that my device is on. So I will apply some kind of potential on this drain, which is greater than your 0. So now I've connected this source to the ground. So ultimately, what have to be the direction of this electric field? That have to be from drain to source. So this is what my electric field direction, and this is my channel length, and correct direction will be ID. Okay. And since I have applied greater than VTH and your VDS is also greater than 0, you will get some kind of channel in between your source and drain. Okay. So if you observe here, your current direction is from your drain to source, right? So you people all know ki in Ohm's law, generally it says ki your J drift will be sigma into your electric field. Okay. So this is the law of point form of your Ohm's law, which is your J is equals to conductivity sigma into your electric field. So what is your current now? Current will be, your drift will be your current by area. In this case, your current will be your drift into your A. So if your current density is depending on your conductivity and your electric field, right? So ultimately, your current will also depends on your conductivity and the electric field. So first, let us see your conductivity. Conductivity of what? Conductivity of your N channel. That is denoted with sigma. So now, your sigma depends on what? Your sigma depends on your number of electrons in the N channel. Conductivity means what? Like the ability of material that it can pass the current, right? So now ultimately what's making this device to pass the current, that is your N channel, right? So you're mainly focusing on your N channel. So this is depending on your number of electrons in the N channel. So how you will increase your electrons at this channel? By increasing your gate voltage. So what is the minimum voltage that you should apply so that we can form our a channel, that is your VTH. So ultimately your sigma will depends on your VGS minus VTH. Whenever you are increasing your VGS, which is greater than VTH, in that case only you will get some channel, right? So this number of electrons will depend on your VGS minus VTH. So now imagine that your VGS minus VTH is something like negative. In that case, there is no conduction that will happen in between this drain and source. Even though if it is zero also, there is no conduction. When your sigma is greater than zero, in that case only, there you will get some kind of conducting path. Is anyone is asking any question or what? Okay, all right. So the next one where the current is depending is your electric field. So your current now, the second one is electric field in between drain and source. Drain and source. So if you know the formula of this, V by L. So what is your voltage? Voltage difference. So that is your VDS. And what is your L? L here is your channel length. So this is what the electric field that will be present in between the drain and source. So if you observe here carefully, your ID now depends on what? For one on this conductivity, and the second thing is your electric field. So your conductivity is depending on VGS minus VTH, and your electric field now is depending on your VDS. So ultimately you should get your drain current with the function of VGS minus VTH comma VDS. So this is decided by your conductivity of N channel, and this is decided by the electric field along the channel length. Okay. So I'll also say the proof maybe in the next classes ki how you will get your drain current. But now I'll directly give the formula which is for triode and saturation region. In cutoff region, obviously your current will be zero. So what is your cutoff region? Whenever your VGS is less than or is equals to VTH, no channel. So we call this transistor is in cutoff region. Cutoff region. So here your ID will be 0. So now whenever your VGS is greater than VTH, there is some formation of channel. So ultimately your transistor is on. Okay. So the first one is your triode region. Triode region means your VDS is less than your VGS minus VTH. Okay. Whenever you're getting this kind of inequality and something that is satisfying this kind of inequality. So we say that our transistor is in triode region. If our transistor is in triode region, our drain current formula will be mu n C ox W by L VGS minus VTH whole square. Yeah, not whole square, sorry. VGS minus VTH into VDS minus VDS whole square divided by 2. So this is what the formula that you will get for your drain current.
Ma'am, can you
And
please repeat once again the last portion? Like
this one,
triode region, triode one.
yeah, triode, I'm not explaining, in deep because if I explain with proof only, you will understand it better. Now, time constraint is there.
Okay.
If I'm there in the next class, definitely I'll explain this drain current. So, whenever your VDS is less than your VGS minus VTH, so in that case, we call this region as your triode region. Okay, if you take some kind of transistor, so if your transistor is satisfying this VDS less than your VGS minus VTH, then you can directly substitute the values in this and you can find out your drain current. Okay, and
Okay.
yeah, I forgot to explain. Your mu n here is mobility of your electrons, and your C ox is your oxide capacitance. Oxide capacitance, it is nothing but your capacitance at your oxide divided by the area. So that is what the oxide capacitance. So, and the units of this is farad per centimeter square. And yeah, remaining everything this is width of the gate and this is your channel length. And yeah, this is fine. The next case is your saturation. Okay, your saturation. Saturation means whenever your VDS is greater than VGS minus VTH. In this case, you got your current equation as half mu n C ox W by L VGS minus VTH whole square. If you observe here, in this point, your current is not depending on your VDS. But previous case in triode region, your current is depending on your VDS. But here only the current is depending on your VGS. Why I'm saying this point is, now no matter what is your drain current after certain point, means if your VDS is crossing your VGS minus VTH, it is saturating to this current. Means if your VDS is crossing your VGS minus VTH, it is giving you the constant maximum current. So this is what the equation that represents. So let us now go to the next one. Right? If this is your capacitance and these are the two metal plates and this is the area is A, and in between you're going to have some kind of dielectric, and the dielectric value may be some epsilon. So your capacitance will be epsilon A divided by what? T. D here is your, sorry,
Distance.
sorry. What happened?
Oh, nothing, ma'am. Nothing. I'm just saying the denominator value.
Okay. Actually, some internet disconnection is there. Okay. So now your C cap is your capacitance divided by your unit area. So that now you will get your C cap as your epsilon divided by A. If you observe this carefully, this is very much similar to your Cox. What is your Cox? Oxide capacitance of the oxide divided by your area of this oxide. So your Cox will be now your C by, what is this? Epsilon by D, right? So I will consider my E as my Eox. So Eox will be generally 3.9 into epsilon naught. Guys, I'm not sure about this value. Maybe it can be 3.9 or 11.7. I don't know. But this is the dielectric value of the oxide into your epsilon naught. So So that is what your E-ox meant. And your oxide thickness is your T-ox. So now it is E-ox by T-ox. So your C-ox will be ultimately your E-ox by T-ox, which is 3.9 into some epsilon naught. I think epsilon naught value is something like 8.85 into 10 to the power of minus 14. Maybe in centimeters it will be that. So 8.85 into 10 to the power of minus 40. So that is the value. So my W by L here, we call this as aspect ratio. And this is really important for design engineers. Uh, they will design this W by L only. They will, try to adjust these values to get the desired output. And your mu and Cox units will be. Okay. So your mu and Cox units will be something like current by voltage square, because your ID will be half mu n Cox W by L VGS minus VTH whole square, right? So what is the units of this? V square. And the units of this is null, because centimeter will ultimately cancel. So now the units of this will be something like, ultimately your current will be either in milliamperes, otherwise microamperes, divided by V square. So this is what the units of your mu and your Cox. Okay, I will conclude with the ID and VDS graph. So if you observe here, this is my triode. Whenever your VDS is less than VGS minus VTH, my current equation is something like mu n Cox W by L VGS minus VTH multiplied with VDS minus VDS whole square by 2. And the saturation region will be something like, if your VDS is greater than your VGS minus VTH, then your current equation is half mu n Cox W by L VGS minus VTH whole square. So when this will occur? This both will occur whenever your VGS is greater than your VTH. Okay. The transistor, definitely it have to be on. So now let us try to draw your ID versus VDS graph. So whenever your VD is like really small, your VDS is really small. I'll imagine my VDS is 0.01. You just try to square it. If you try to square your VDS, what you'll get? You will get your you'll get your VDS square as 0.0001. If you try to substitute that, this is very much equivalent to 0. So whenever your VDS is very small, you can neglect this VDS square by 2 term. Neglect your VDS square by 2 term. In this case, your ID is directly depending on your VDS. So up to here, this is linear because it is directly proportional, and it is very much similarly looking like your y is equals to mx. To this point, to certain point, it is having this linear property, and we call this region as deep triode region. Deep triode region. After that, you have to consider your VDS. If you see here, your ID and VDS now is looking like a quadratic sort of, right? So after that, there is a quadratic form. Whenever your VDS is crossing your VGS minus VTH, in this case, your ID is not at all depending on your VDS, no matter how much you apply your drain current. So now you're getting some kind of constant current. Okay. So your ID is constant, and this is the maximum current that you can get here. This is like in saturation. You can also call it as an ID SAT. ID SAT. So this is what the graph of ID versus your VDS. So I think I'll stop here. Okay.